lecture we continue the discussion on the bin packing problem. The application to transportation model comes from assuming that we have a central warehouse and we have to transport to a large number of retailers or customers, and there is a point to point transportation, which means say a truck will go from here to this and then it will come back to the starting point and then it will go to the next customer after picking up material from here and so on. So, the distance or time the truck takes from the warehouse to customer J can be given as Dj or Cj or Tj if it is the time taken. So, this time would include the loading, the unloading as well as the transportation time. Now, given n customers where customer J requires a time of Tj, and if a vehicle is available for T time units, the problem is to find out which of these customers or orders will be allotted to each of these vehicles such that the number of vehicles is minimized and the sum of the Tj's allotted to each vehicle will be less than or equal to T. As mentioned in the previous lecture, this reduces to what is called a one dimensional bin packing problem, where the one dimension is time here, time required by each of the customers to be compared with time available with each of the trucks. So, the problem is to find out the minimum number of trucks. Now, we explain it through a numerical illustration. So, we would So, we assume that there are 10 requirements and the time for each of these requirements are given in these 10 numbers and then the total time availability is 80. So, the problem is to find out the minimum number of trucks such that we are able to meet all the demand. So, now Tj is given here. Now, we have to find out which of these items. Now, we can treat each one of these as items that go into a bin. The bin's length is 80, items have lengths 11, 73, 13, 37 etc. So, which of these items will go to which of these bins such that we minimize the number of bins as well as ensure that the length of the items that go into a bin does not exceed the bin length. So, we have seen the formulation in the previous lecture. So, we will now assume that Yj equal to 1 if bin j is chosen and Xij equal to 1 if item I goes to bin j. Now, we know that with 10 bins we can definitely meet all the requirements. So, we are going to assume that there are a smaller subset of y1 to y10 which we would like to minimize. So, the objective is to minimize sigma yj where yj equal to 1 if bin j is chosen. This depends on the notation. Now, here we are using j for the bin and I for the item. Therefore, summation yj j equal to 1 to 10. Now, each bin each item is to be associated to only one bin. So, sigma xij summed over j is equal to 1 for every I, which means each item I will go to exactly one bin. And then for each bin, Ti xij is less than or equal to 80 yj. Now xij equal to 1 if item I goes to bin j. So for a particular bin, sum of the xij's is the number of items that are attached to that bin. Sigma Ti xij is the length of the sum of the lengths of the items attached to that bin. So this is the sum of the lengths of the items attached to bin j, and this should be less than or equal to 80, and we can assign I to j only when it is chosen, only when yj is 1. Therefore, this constraint less than or equal to 80 yj or capital T yj will ensure that the not only items will be assigned to bins that are chosen, it will also ensure that when items are assigned, the sum of the lengths does not exceed this 80. And then we have yj and xij as binary variables. Now this is a binary integer programming formulation. This can be solved optimally using an IP solver. But right now, as I mentioned, for 10 items we will have 10 variables here and 100 variables here. So we will have 110 variables. And then there will be 10 constraints here, there will be 10 constraints here. So there will be 20 constraints. Now this constraint is for every item, this constraint is for every bin. So there will be 110 variables and 20 constraints. So in general, if there are n items, we would have n square plus n variables and 2n constraints. Now we can solve this optimally, and when we solve this optimally, we would get a solution which would be like this: y1 equal to 1, y1 equal to y2 equal to y3 equal to y4 equal to 1, which means 4 bins are chosen. So the item with 73 goes to this bin, items with 11, 13, 37 and 19 go into this bin. The item with 51 and 29 go into this bin, and the item 17, 39 and 23 go to this bin. So the solution will be, this will be x, this is item number 1, so x1 1, x3 1, x4 1 and x10 1 and so on. Now the sum of these is 11 plus 19 is 30, 43, so 80, 73, 51 plus 29 is 80, 17 plus 39 is 56, 56 plus 23 is 79. So we find a solution with 2 80s, a 79 and a 73. Now let us assume we want to solve this using heuristics. Several heuristics are available, we will see one or two of them. So most of these heuristics first sort these items in the decreasing order. So when these items are sorted in decreasing order, we get 73, 51, 39, 37, 23, 29, 23, 19, 17, 13 and 11. So, we first apply a very commonsensical heuristic. So, we take the first item and then we observe, we create a bin. So, we say bin 1 and put the first item 73 here. Now, we take the second item and see if that would go into the bin. 51 will not go into the bin because the length of 80 will be exceeded. So, create a second bin. So, bin 2 has 51. Now, take the third item which is 39 and see whether it will go into this bin first, it will not go, and then see whether it can go into this bin. 51 plus 39 does not go into this bin. So, create a third bin, bin 3 with 39. Now, take the fourth item with 37. So, it will not go into this bin because the length will become 110. It will not go into this bin because the length will become 88. It will go into this bin. So, 39 plus 37 with length equal to 76. Now, take the next item 29, see it will go to this bin, it will not go, then try this bin. So, it fits in. 51 plus 29 is equal to 80. Now, look at the sixth item with 23, it will not go into this bin, it will not go into this, it will not go into this, create a fourth bin with 23. Now, take the next one 19. So, 73 it will not go, again it will not go, again it will not go. So, 23 plus 19. Now, take the item with 17, it still will not go because this will be 90, it will not go into this bin, it will not go into this bin, it will go into this bin. 23 plus 19 is 42, 42 plus 17 is 59, so it will go into this bin. Now, look at the 13, it will not go into this bin, it will not go into this bin, it will not go here. Now, here it is 23 plus 19 42, 42 plus 17 is 59, 59 plus 13 is 72, so it will go into this bin. And then take the last one, it will not go here, it will not go here, it will not go here. Now, let us see, this is 72, so it will not go here. So, create a fifth bin with 11. So, now this method gives us 5 bins, whereas the optimum gives us 4 bins. It is a heuristic method, it does not guarantee optimum all the time, therefore, it would do that. Now, this method gives us, it is a minimization problem. So, a heuristic algorithm would give what is a feasible solution to the problem will be an upper bound to a minimization problem. So, the number of bins 5 is an upper bound to the optimum value which is 4. Now, this is a very popular heuristic, this is called the next best decreasing heuristic, next fit decreasing heuristic. It is called the next fit decreasing heuristic. Important thing, it is a decreasing heuristic because the items are already arranged in decreasing or non-increasing order, therefore, it is a decreasing heuristic. In fact, this is called the first fit decreasing heuristic. Sorry. This is called the first fit decreasing heuristic, which means every item we see, we take it, we see whether it will go to the first bin, if not we will see whether it will go to the next bin, and then it will go to the third, and then so on. So, whichever it fits first, it will be put there. So, it is called a first fit decreasing heuristic. Now, we have other heuristics, some of them are called best fit decreasing heuristic and so on. So, if there is more than one where it can fit, now at that point we try and fit it into the one where it fills up to the maximum, that is called a best fit decreasing, and then the worst fit decreasing would be if there is a choice, put it in the bin where it would actually fill the minimum after filling. So like that we can develop different kinds of heuristics for this particular problem. Now one of the advantage of using this heuristic is, now here we have a solution with 5 bins, so we know that there is a solution with 5 bins, and once we know that there is a solution with 5 bins or 5 trucks in this example, we are only interested in solutions which are 4 or lower, because we already have a solution with 5. So using a very simple heuristic like this, we get 5 bins, and if we still want to solve it optimally and we want to check whether 4 is possible, then we have to come back and solve this optimization problem. But the nice thing about this is, now we do not have to define j equal to 1 to 10, it is enough to define j equal to 1 to 4. Because we already have a solution with 5, so it is enough to define j equal to 1 to 4, and now see that simply define yj equal to 1 for j equal to 1 to 4 and xij equal to 1 if item I goes to bin j. So we will have 4 plus 40, which is 44 variables, and then we will have 14 constraints, n square plus n. No, here it will change now, this will not be n square plus n. Now here the number of variables yj will be 4, xij will be 40, so we will have 44 variables, and in terms of constraints, this is for every I, so there are 10 constraints, this is for every j, there are 4 constraints, so there are 44 variables and 14 constraints. Whereas in the old formulation, if we used 10 bins, then we would have 110 variables and 20 constraints. So here are a set of problems where it is actually advantageous to solve it using a heuristic first, and then based on the heuristic solution, if we approach the optimization, we observe that the number of variables and constraints in the optimization will come down. So that is one advantage of using this heuristics. At the same time, if we are all right with the heuristic solution, then we could say that, well, this solution would be acceptable to us. But if we actually look at this solution and then we can tweak this solution, now that is not part of the best fit decreasing heuristic. The best fit decreasing heuristic would stop here because it is interested in minimizing the number of bins, and this heuristic gives 5 bins. But then we could do many things. If we look at the loads, it is 73, 80, 76, now this will become 72 and this is 11. Now we can do a few more things by adjusting some of them. By a little adjustment, one can try and actually reduce the number of bins from 5 to 4. But if we were to implement this solution, particularly for our truck example, then we observe that one truck is going to be used for 73 minutes, another for 80, 76, 72 and 11. So when we start applying this heuristic to the situation that we are talking about, we are also interested in some kind of a load balance among the trucks, because it is also hard to say that one truck will be utilized only for 11 minutes while few trucks are utilized for 80, 76, 73 and so on. So we also need to have a secondary load balancing objective if we were looking at solving this kind of a problem. We can do a few more things. We can actually relate this problem to a traditional machine scheduling problem. In fact, we can try and do a few more things. Now if we want a solution with a better load balance for 5 bins, we can try something else. We can now look at something like bin 1, bin 2, bin 3, bin 4 and bin 5. Now we will go back and put the 73 here. Now the next one will not go to this bin, we will put a 51, we will put a 39, we will put a 37 and then we will put a 29. And then the next one we can put a 23, so it will come here. So 29 plus 23 is 52. Now 19 will come here, because if we see where we assign, for example here, now at this point the first 5 go to the first 5 bins, the sixth one is 23. So 51 plus 23 is 74, 39 plus 23 is 62, 39 plus 23 is 62, 37 plus 23 is 60, and 29 plus 23 is 52. So the best place to put the 23 is here, because the loads will get balanced. Even though we can put that 23 here, which will be closer to 80, but then we realize that the loads will be unbalanced, and then there will be a load imbalance. Therefore, the best thing to do is to put that 23 here, so that the loads are also balanced as they can be. So we put this 23 here to get 52. Now the next one is 19. Now if we look at the loads are 73, 51, 39, 37 and 52. So this is the smallest, so we get better load balance by putting this 19 here. Similarly, the 17 will come here, the 13 will come here. Now this 11 cannot come here, because 73 plus 11 is 84. Now we check this is 64, so this can take that 11, this is 56, this is also 56, this is 52, so this will finally take that 11, and now the loads for 5 bins will be 73, 64, 56, 52, sorry, 56, 56 and 63. So now we have a solution. If we were to use 5 bins, then this is a solution with better load balance than this. So depending on the problem and depending on more than one objective, we can use suitable heuristics. Now the same problem we can try something more and see that if we have 4 trucks or bins, what happens to, and if we start allocating this 10, what happens to the loads? So 73 will come here, 51 will come here, 39 will come here and 37 will come here. So automatically from a load balance point of view, 29 will go here, because this is the smallest load. 37 plus 9 46 plus 20 66. Now 23 will come here, 39 plus 4, this will give us 62. Now 19, this is 51, so 19 will come here, 51 plus 19 is 70. 17 cannot come here because it will exceed. Now to put this 17 also will not come, 17 can come here, 51 plus 19 is 70, so it will 7 plus 17 will exceed. 39 plus 23 is 62, so 62 can handle this 17, this is 66, so this will get this 17 and this will get this 13, and then we do not have a place to put this 11, because the load will exceed 80 if we add 11, here also it will exceed 80, here the load will be 62 plus 17 79, it will exceed 80, this will become 66 plus 13 79, it will again exceed 80, but then we have to put this 11 somewhere. So we can put this 11 here and then say that this is 73, this is 81, this is 12 plus 7 19 79, this is 12 plus 7 19 79. Now we realize that the optimum solution was able to give us 80 73 80 79, the heuristic solution gave us 73, 81, 79, 79. So using this heuristic solution, now we observe that we won't be able to squeeze all the orders in 80 time units if we have only 4 trucks, or if we use this heuristic and if we want to minimize the number of trucks such that I can squeeze everything into 80, the answer is 5, whereas the optimum is able to squeeze all the 10 items into 4 trucks or 4 bins such that the length is 80. Here it says it requires an additional length of 81. Now we can either solve this optimally, this is easily the best thing that we would like to have, but in the absence of solving the integer programming optimally, and if we rely on heuristic solutions, then we have to understand here at times we could get even the optimum solution through some of the heuristics. We can try several heuristics. Now we will be able to minimize the number of bins for a given length, and then within that we may be able to get a load balance, and we may also say given certain number of bins, what is the length of the bin that I require. Now it happens to be 81, what is the minimum length that I require. Now this problem is equivalent to the machine scheduling problem. It is called a parallel machine scheduling problem. Now for this particular example, if I force 4 bins and then apply a load balancing algorithm, it says that I may require 81 minutes on one of the trucks or one of the bins, whereas the optimum is able to do it within 80 minutes. Right. We next move to the traveling salesman problem. Now here what we do is we assume that there is a central warehouse, and then we have a set of customers now this is like the equivalence of where we look at milk run. So we start a truck from the warehouse, and then we meet the requirements of all these customers in one trip, which means that even if each of these have a requirement, the sum of all the requirements is less than or equal to the capacity of the truck, or theoretically or mathematically we can assume that the truck has a very large capacity which is close to infinity and can handle the requirements of all these customers. Practically we would say that we know these requirements and the truck capacity is higher than the requirements of all of these. In such a case, the truck will start from the warehouse, visit each customer once and only once, deliver, and it will come back to the warehouse. Now that is called the traveling salesman problem. Now if we assume one warehouse and 6 customers, we have 7 points, we can assume that we will have a 7 by 7 distance matrix, and then starting from W, we want to visit each customer once and only once, and then we come back to the starting point. Now we have already seen several aspects of the TSP in the advanced operations research course, where I have given the formulation for the traveling salesman problem, and also I have explained many 2 or 3 different types of branch and bound algorithms to solve the traveling salesman problem, and I have also looked at a lot of heuristics extensively in that course where we have studied the traveling salesman problem in detail. What we will do now is we will take another look at the formulation of the TSP, and then we would also look at some heuristics, and I would also try and give you some of the optimum solutions to the traveling salesman problem. I will make it a little brief because a more elaborate treatment is available already in the other course. We have already seen this formulation of the travelling salesman problem. Now Xij equal to 1 if the salesman visits city J immediately after visiting city I. Now Dij is the distance matrix. Now again in the context of the travelling salesman problem, we will assume Dii, that is distance between a point and itself, to be infinity and not 0. So distance between a point and itself is so large that it does not visit the point immediately after visiting it. For example, if we put D11 and D22 etc. to be infinity or very large value, the variables x11, x22, x33 etc. will not be in the solution. Now this will ensure that if a salesman is in a particular city, Xij equal to 1 summed over j, which means if the person is in a particular city, the person has to visit only one city immediately. So that will be taken care of by this. And if this person is in a particular city, he or she should have come from one city, so that is taken care of this. But then we need the extra constraints, otherwise the TSP will become an assignment problem. Or if we have 5 points including the warehouse, it may give solutions like this, which means it goes from say 1 to 2 and then 2 to 1 and then the salesperson suddenly goes 3 to 4, 4 to 5, 5 to 3. Now they will satisfy this. So this will be like solution to the assignment problem. Now things like this are called subtours and these have to be eliminated. The solution to the TSP is always a full tour, which means you will have a solution like 1, 3, 4, 2, 5, 1. This is called a full tour. 1 to 2, 2 to 1, 3 to 4, 4 to 5, 5 to 3 is called a subtour. So we need this, plus we have what are called subtour elimination constraints. Subtour elimination constraints called subtour elimination constraints. Now if there is a subtour, let us say there is a first we define ui minus uj plus n xij less than equal to n minus 1, and then we define it for I equal to 1 to n minus 1, j equal to 2, 3 up to n, and I not equal to j. Now if there is a subtour, let us say there is a subtour 1 to 2 and 2 to 1, or first let us assume that there is a subtour which is 3 to 4, and then let us say for a 5 city problem there is another subtour that is 1 to 5. So a subtour 3 to 4 will be eliminated here because there will be a constraint which will say u3 minus u4 plus 5x34 is less than or equal to 4, and u4 minus u3 plus 5x43 less than or equal to 4. There will be a constraint like this, where I have just written ui minus uj plus n xij less than or equal to n minus 1. Now if such a subtour exists, then these two constraints have to be satisfied. Now we realize that adding vertically, you get, if both are equal to 1, you will get 10 less than or equal to 8, which is not true. Therefore this constraint will ensure that subtours involving say a 2 city subtour or whatever 3, 4, 4, 3 are automatically eliminated. The same thing will hold for any, for example, if we have 3, 4, 5, then there will be u3 minus u4 plus something, u4 minus u5 plus something, and u5 minus u3 plus something. So, vertically adding it will give us an inconsistent set. Therefore, all these subtours involving this and this are eliminated. Now, if there are subtours that involve city 1, the reason 1 is important is because of this I equal to 1 to 2 to n minus 1, j 2 to 3 to something. So, if there is a subtour involving city 1, then that subtour apparently one will get a feeling that it will not be eliminated by this. For example, if we start writing for this, then you will get a thing like u2 minus u1 plus 5x21 is less than or equal to 4. In fact, u1 minus ui minus uj, so u1 minus u2 plus 5x12 less than or equal to 4, but then you do not have a 2 1 because j is not defined for 1, so you will not get a second constraint. But the way we understand this is, if there is a subtour that involves 1, then there has to be another subtour, at least one more subtour which does not involve 1, and since all subtours not involving 1 are eliminated, automatically subtours involving 1 will also be eliminated. Now, this will not violate a full tour, because a full tour will have something like this: 1 to 3, 3 to 4, 4 to 2, 2 to 5, 5 to 1. Now, that 5 to 1 constraint does not exist in the formulation, therefore, you will have only 4 constraints here, you will not have 5. Now, the ui's and the uj's can be so defined such that this set of constraints will be satisfied. So, this set of constraints are called subtour elimination constraints, and they are used extensively if we have to solve a TSP optimal. But having said that, this TSP is usually not solved as a mixed IP, because this is a mixed IP. You realize now that ui's are greater than or equal to 0. Now, if there are n cities, then we have n square variables for xij. So, there will be n square variables for xij and n variables for ui. So, we will have n square plus n variables, where these are binary and these are continuous. And in terms of number of constraints, now we will have n constraints here, we will have n constraints here, we will roughly have about nc2 constraints, slightly less than that, maybe nc2 minus n constraints and so on. So, we will have the order of nc2 constraints here. So, this will still become a large problem when the number of cities increases, and this would roughly increase of the order of n square. So, we will have a large number of constraints, and this is a binary formulation plus a mixed formulation, because these set of variables are continuous. So, we normally do not use this formulation to solve the travelling salesman problem. Instead, we use branch and bound algorithms. There are several types of branch and bound algorithms that are available. The more popular one is the one by Little and 3 other authors. Now, this is based on the penalty approach. I have given a detailed description of the Little's branch and bound algorithm in the advanced operations course, and hence I am not repeating the Little's algorithm once again here. So, the reader, the viewer could go to the other lecture and take a look at the Little's algorithm through which we can solve this. Now, several heuristic algorithms are very popular for the branch and bound for the travelling salesman problem, and for the purpose of completion, let me just explain 1 or 2 heuristic algorithms here. So, we take a 5 city TSP and explain through this. So, a 5 city TSP with distance matrix is Z dash 10, 8, 9, 7, 10 dash 10, 5, 6, 8, 10 dash 8, 9, 9, 5, 8, 6. Now, here we have to assume that there is a warehouse and there are 4 other places that we have to visit. So, one could be the warehouse, 2, 3, 4 and 5 could be the customers. In fact, in a TSP it does not matter, because the solution 1, 2, 3, 4, 5, 1 is the same as a solution 2, 3, 4, 5, 1, 2. Therefore, it does not matter where the truck actually starts, but then it is customary to say that it starts from the warehouse and it completes one round by visiting each and every customer once and only once, and then it comes back to the starting point. Now, the simplest heuristic is called the nearest neighbor. So, assume that I am in city 1. Now, I go to the nearest neighbor who is 5. From here I go to 5. Now, from 5 I go back and realize I can go to 2 or I can go to 4. So, I go to 2. Now, I come to 2 and the nearest person is 4. Now, I have only 3 remaining. So, 3 and 1. Now, the length of this will be 1 to 5 is 7, plus 5 to 2 is 6, plus 2 to 4 is 5, plus 4 to 3 is 8, plus 3 to 1 is also 8. So, this is 13, 18 plus 8, 26 plus 8, 34. We do not know whether this is the best solution or we could make this solution better. So, we simply expand this by trying that we start with 2 first. So, I start with 2. So, I go to 4, this is the minimum. From 4 I realize this is the minimum, but I have already visited 2. So, I go to 5, and from 5 I go to 1 and then 3 and then 2. So, this will be 5 plus 6 plus 7 plus 8 plus 10. So, this will be 11, 18, 26 plus 10, 36. Like this we can do a nearest neighbor with each of the cities as the starting city, and then we can proceed and then choose the best out of these solutions that we have. In this example we can show that this is actually the optimum solution, and the nearest neighbor is able to give the optimum solution right away when we start from 1. This is because of the nature of the numbers that we have in this particular example. Another very popular heuristic is called the 3-opt heuristic. The 3-opt heuristic essentially does a 3-way exchange. So, what we do is, if you have a TSP, let us say a large TSP, if we have a large TSP, now let us assume this is a solution. So, 1, 2, 3, 4, 5, 6, 7, 8, 1. This need not be the optimum or the best solution. This is a TSP with 8 nodes or 8 cities. Now, I take a solution like this, and then I take one of these as AB, another pair as PQ, and the third pair as UV. Now, we realize there are 8 nodes. So, AB, PQ, UV can be chosen in many ways. You would also realize this is AB, this is PQ, but then I left a node and I have chosen UV here. Now, using this I can actually create some feasible solutions. For example, I can remove this, I can remove this, and I can remove this. Now, I can do this, I can add these two, I can add these, and I can retain this. This will be another feasible solution. For example, I can remove this, I can do this. This could be another solution. So, like this we have several possible solutions. So, if we have a AB, PQ, UV, then we can actually get 7 more solutions to this. We can have AB, PU, QV, AP, BQ, UV, AP, BU, QV, AQ, UB, PV, AQ, UP, BV, AU, QB, PV, AU, QP, BV. So, for every AB, PQ, UV chosen, we can have 7 solutions. Now, if there are n, we take a starting solution. So, there are n vertices, there are n edges in the solution. So, AB, PQ, UV represent 3 out of the n. So, they can be chosen in NC 3 ways, and then for each of these AB, PQ, UV we can write 7 more solutions from this. So, if we are given a TSP with say 5 vertices, then 5C3 is 5C2 which is 10, 10 into 7 we can get 70 solutions out of this. The only thing is, because we have 5, then we realize that these 70 are not unique, there will be overlap, because when we have a 5 by 5 to choose A, B, PQ, UV, then some of them have to overlap. So, a lot of those 70 will overlap, but then we can still choose the best of them and we can proceed. Whereas, if we have a problem with 10 vertices, now you realize that A, B, PQ, UV itself can be chosen in 10C 3 ways, 10 into 9 into 8 by 6, another 7. So, for every solution we will be able to do this. So, we have 800 and 12 sevens are 84, we have 840 solutions which we can get from a single solution, and then we can keep improving this. So, 3-opt is a very popular method. One can write a simple computer program which would do the 3-opt heuristic, and then we could get the best values of the solution. But then when we apply these ideas particularly to trucks and distribution and so on, we also need to look at a little beyond this kind of a TSP and then add a few more aspects to the TSP. Now, this TSP is symmetric, which means distance between I to j is the same as j to I, but then when we actually apply these on practical problems, we understand that actually the distances are not the same, because there could be one ways and there could be different highways that you need to take when you go from one place to another. So, we have TSPs which are not symmetric. We also observe that particularly in critical distributions like say mail motor and other such distributions, one would observe that actually even if the routes are the same, the time taken to go from one place to another will depend on the time of the day when the travel is made. So, the travel is made early in the day, one can reach a little faster, and when we move into peak hours, then we go much slower. So, there is a speed dimension that comes in, there is a distance, the speed from which the time is to be computed, and the speed will depend on the time of the day, because most of these also at the end of the day result in problems where certain delivery times have to be met and so on. So, we have to take into account speed of the vehicle also. We also could have windows, time windows, where delivery to a customer has to be made either before a certain time or after a certain time or within a time interval. So, all these result in handling the travelling salesman problem very effectively in terms of the nature of the objective function, in terms of additional constraints that we may have, also in terms of getting the data depending on dynamically updating and getting the data, so that the correct data is used and the corresponding TSPs are formulated and solved. The next thing that we will have to look at is called the vehicle routing problem, where we would have a central warehouse, we would have a set of customers. Now, we realize that the demand of these customers is such that we may require more than one trip. The vehicle capacity cannot handle the demand of all of them. So, we get into a situation of which customer goes into which trip, and then how the trips are made. Now that problem is called the vehicle routing problem. A solution to vehicle routing problem could be one trip will be like this and the other trip would be like this, but in general which cities or customers will go to which vehicle, such that we minimize the total distance, we use minimum number of vehicles and then we are able to meet the demand, is called a vehicle routing problem. We will see various aspects of the vehicle routing problem in the next lecture.